Okay, so looking at number 42, 42 talks about Big Ben, and it talks about the hour and the minute hand. So I'm going to separate them out. We'll talk about the hour hand first. I'm going to put hour here. And so I know the mass. The mass of the hour hand is 60 kilograms. It also gives me the length. The length, they tell me, is 2.7 meters long. And the other thing I know is that the hour hand, I can find out its angular velocity. The way I can do that is like, okay, so if this is my complete clock here, my hour hand will start here at 12, and it's going to go all the way around, and it's going to go all the way around in 12 hours. So it's going to make one rotation, which is 2 pi radians, and it's going to do that in a time of 12 hours. It goes around twice a day. Now I converted that over to seconds, so 12 hours times 60 minutes, or 60 minutes an hour times 60 seconds in a minute, which gave me 43,200 seconds. So my angular velocity is going to be 2 pi radians divided by the 43,200 seconds, and if I calculate that all out, I'm going to end up getting 1.45 times 10 to the negative fourth radians per second. For the minute hand, they give me that as well. There, they told me the mass was 100 kilograms. They give me a length now of 4.5 meters. And now, again, same equation, same scenario. Angular velocity, it's going to go around once, so that's 2 pi. But now it's only going to take 1 hour to go all the way around, so that's going to be 3,600 seconds. So my angular velocity for the minute hand is going to be 1.745 times 10 to the negative third radians per second. Okay, and you can double check the math on that, but we did one rotation, so 2 pi rads, and we divided by the time it took to go around for each. Now, they want us to find the angular momentum of these. So remember, angular momentum is equal to I times omega. Well, we need to find the momentum, the moment of inertia for the hour hand. Well, because this is a rod rotating about the end, and you can go look this up in the notes, but the moment of inertia in that case is going to be 1/3 ml squared. Okay, and this is in our notes, and I would give it to you on a quiz or something like that, so you don't have to memorize this one. So what I'm going to do is for L, I'm going to go 1/3, or something. Let's find the I first. So my moment of inertia is 1/3 ml squared. So this would be 1/3 of the mass, which was 60 kilograms, times the length, 2.7 meters. Don't forget to square it. And so my moment of inertia for the hour hand is going to be 145.8 kilogram square meters. I can now find my angular momentum by doing I times omega. So my 145.8 kilogram square meters times my angular velocity, which is 1.45 times 10 to the negative fourth radians per second. And so I find my angular momentum of the hour hand to be 0.0212 kilogram meters squared over seconds. I can do the same thing for the minute hand. Find that, again, L is equal to I omega. Find the moment of inertia using the 1/3 ml squared. And now this time, my mass is going to be 100 kilograms. And I'm going to multiply that by my distance, which is now 4.5 meters. Don't forget to square it. And so my moment of inertia of my minute hand kicks out to be 675 kilogram square meters. Again, double check my math on that just to make sure I'm right. So if I want to find my angular momentum, L is equal to I times omega. So 675 kilogram square meters times my omega, which is 1.745 times 10 to the negative third radians per second. And so my L in this case comes out to be 1.18 kilogram meters squared over seconds. Now, the question asks for the total. So what we're going to do is now we're going to add these two together to get an L total for the system, which comes out to be 1.2, when we round it, kilogram meters squared over seconds. So that's our final answer for number 42.